Good morning. For the last 2 or 3 classes, we were discussing about Diels-Alder reaction under our cycloaddition. So, today what we will do is that we will discuss one more reaction which we call as Ene reaction. Fine. So, in Diels-Alder I said Alder was the student of Diels and he was working together with Diels and they ended up in finding out your Diels-Alder reactions. And Alder with other co-workers discovered similar type of reactions which we call as Ene reaction, or you can also call it as Alder Ene reaction. So, what this reaction is exactly about? You take an allylic system, okay, with your alkene and you heat this reaction. Okay. So, what happens is that you end up with a product where you have a shift of this hydrogen to here. So, this particular reaction is called as an Ene reaction. Basically, if you want to push the arrows, you can take it here with and with this. Okay. This is your Ene reaction. This Ene reaction can be compared with it has a similar feature with some like 4 or 3 reactions which we can see. For example, if I had taken this type of Ene and you have 2 Enes here, okay. One is your allylic system, another is Ene. If we connect this 2 system, okay, by an S bond, then if you view this reaction mechanistically, how this will look like, how we can see this reaction mechanism if we can connect this 2 alkene system by an S bond and then you view this system, how this looks like. Exactly, yeah, this you can see as a 1,5 hydrogen shift. So, in reactions mechanistically more or less similar to your 1,5 hydrogen shift, where if you in Ene reaction what happens, you take this 2 Ene system separate, but in 1,5 hydrogen shift what happens, these 2 alkene systems are connected by a S bond, so that your alkene is conjugated and then you have this hydrogen shift. But in Ene reactions they are separate identity and then you have an hydrogen shift, but this mechanistically you can compare this Ene reaction with your 1,5 hydrogen shift. That is how you can look this Ene reactions, to keep in mind. Now, there are some other way you can look this reaction. Okay. For example, I am taking the same reaction, my Ene, with an alkene, so you get a nice system like this. Okay. Now, I can call this how many, if you see the electron push, how many electrons are totally involved. If you see my allyl system, okay, I can say that 4 pi electron systems are there, is involved in the reaction for this identity, okay, for this substrate. For alkene I can say 2 pi electron system. So, what it essentially means to me is that, can I call this 4 pi electron system and 2 pi electron system, can I relate it with the Diels-Alder reaction, because in Diels-Alder reaction you have a diene, right. We call this as a diene system which is a 4 pi electron system, and you will have a dienophile which will be 2 pi electron system. Same way we can take this as your, in this case we will call it as Ene, because it is not a diene system, it is an Ene system, and this we can call as similar to dienophile. Okay. So, you have an ene plus dienophile, and then this system should be what this addition should be. It should be 4 plus 2 cycloaddition based on Woodward-Hoffmann rule. Right. So, how this is now similar? This is now more or less similar to your Diels-Alder reaction. So, you can look your ene reaction as 1,5 hydrogen shift mechanistically, and in other way with respect to substrates, you can look this reaction more like a 4 plus 2 cycloaddition, similar to your Diels-Alder reaction. Two ways of looking this ene reaction. It has some similarity with your 1,5 hydrogen shift, it has similarity with your Diels-Alder reaction. Clear? Okay. Then now, so we know that how this mechanism works. It is nothing but it is a 4 plus 2 cycloaddition reaction. So, your ene reaction is nothing but it is a 4 plus 2 cycloaddition reaction. Now, we will see whether this addition is suprafacially favored or intrafacially favored, whether heating may, or in thermal activation whether it is suprafacial or in photo how it works, okay, in reaction. So, for that to understand it, it is better to understand based on your HOMO-LUMO interaction. Just since it has a similarity with your Diels-Alder reaction, we will just take your Diels-Alder reaction and we see how we can understand, compare it with your ene reaction. In Diels-Alder reaction, you have a butadiene and you treat it with your alkene. So, what you are talking about? You are talking about the HOMO of your butadiene and you are talking about the LUMO of your alkene. So, if we draw the structure more likely, okay. So, we will draw the HOMO of your butadiene. Okay. Then we will draw the LUMO of your dienophile. So, this is your HOMO of butadiene, this is LUMO of your alkene, that is your dienophile. Okay. And you know that in Diels-Alder reaction it nicely goes your suprafacial. So, by activation, thermal activation, you end up with a nice suprafacial cycloaddition. So, we normally we write this reaction as pi 4 S plus pi 2 S. So, this is about Diels-Alder reaction that we have studied in detail. Now, we will see whether we can relate this with your ene reaction. Okay. So, case of ene reaction, what happens? You are going to take an allylic system, okay, and then you treat it with an alkene, fine. So, how you can think about the HOMO and LUMO of this? Same way, since it is an allylic system, okay, we will be taking the HOMO of your ene. So, we will be taking the HOMO of your ene. Only one thing is that it has an Okay, this should be the HOMO of your ene system, right, and you have an hydrogen here. Okay, that is fine. So, then you will be drawing the LUMO of your alkene. So, it will be LUMO, HOMO of ene and your LUMO of your alkene. Now, again you can see nicely it undergoes again like Diels-Alder reaction, it is suprafacially favored. On thermal activation, that is why on thermal activation your Diels-Alder reaction also nicely goes and your ene reaction also goes nicely. So, it is suprafacially favored. Do not worry about this hydrogen because it does not have a node. So, so it should be a suprafacially favored reaction. But how to represent this? Like pi 4s plus pi 2s, you cannot write like this because there are not 4 pi system included in your ene. Ene you can write that, the best way of writing is pi 2s plus pi 2s, this is ene ka pi 2, this is alkene pi 2 plus sigma 2s, because you are talking about sigma orbital here. So, you can represent as pi 2s plus pi 2s plus sigma 2s, because s is, you know that it is more like a suprafacial system. So, it is similar to a Diels-Alder. So, your ene reaction most like it also you can think about a diene, instead of diene you are thinking as an ene, and dienophile remains as your dienophile, okay, and then it is suprafacially favored. So, 2 ways to understand ene, one is based on Diels-Alder, another based on your 1,5 hydrogen shift. Okay. Fine. Now, what we will do is that we will see some examples on some good examples of ene reactions. First, we will take the simple example. So, I have an put with an anhydride, so you have an hydrogen pulling, then you can shift this with this, you can get your stuff, all right. Yes, so this on eating, you can say it is pi 2s plus pi 2s plus sigma 2s, and your product, you can write your product. And this is the hydrogen which has been shifted, okay, migrated, and this migrates suprafacially, okay, more like your 1,5. Even you can your pinene system works with this, right? Pinene system, you can take your pinene system, which is a very good example to work with your ene reaction. You can think about working with this type of pinene, beta pinene system. So, so what hydrogen you are going to consider here, because your hydrogen should be allylic. So, you are going to talk about this hydrogen. So, this can abstract an hydrogen, this can get here and you can have your reaction. So, you will get a product which is okay. I can take these 2 examples which are good to do your ene reactions, fine. But in both these examples, if you see your dienophile, okay, we are talking dienophile more about your ene system, that is your alkene system. Okay. There are very good number of ene reactions where your dienophile will be a carbonyl system. Okay. We will see that first variant of your ene reaction. We can call them as carbonyl ene reaction, good variant of ene, where your dienophile is carbonyl group, right. So, the best example, if you have an hydrogen plus the system. So, what happens similar like a ene reaction, just like say ene reaction. Okay. So, just a variant of ene. So, this is your ene you are talking about, and this is your dienophile you are talking about. So, eating you get your product. This is your carbonyl, people call it carbonyl ene reaction, where your dienophile is carbonyl functionality. Can you relate this carbonyl ene reaction with any other reaction? Any similarity with any reactions which you have studied, this carbonyl ene reaction? Some good reactions. So, carbonyl ene reaction as from the product point of view, yeah, that is more important, from the product point of view, not based on your reaction mechanism, but the product form of view. Prince reaction, carbonyl ene reaction and Prince reaction, from the product point of view they will be more related. For example, if I see this reaction, you have a carbonyl with my alkene system. Okay. This is your ene reaction. So, I end up with a product like OH. Okay. This is your ene, carbonyl ene reaction which you have studied. Same way, if you think about your Prince reaction, it also is more like a carbonyl dienophile with your, but your alkene you are talking about is different. Okay. Just from the product point of view, just to relate, okay, not from the mechanism, just from the product point of view, carbonyl ene reactions can be related with your Prince reactions. Fine. Okay. Can we do a carbonyl ene reaction now? For example, I give you this reaction with oxide. Can you think about the reaction now? This reaction you can carry out in titanium. So, this should be your, which should be your now dienophile and diene. So, that's will be interesting when you talk about the ene reaction. So, this will be your dienophile, okay, and this will be your diene. Okay. So, to understand better, we can, if you write methoxide carbonyl, you can have an hydrogen this, right. I can write the same reactions in this way. Then after that it is easy, because then you know how to push your, you end up with a get a nice product, okay, looked as an in reaction. So, that's what we have seen about your in reaction, and this is your carbonyl in reaction. So, you have seen one of the variant carbonyl in reaction. In and carbonyl in reactions. Okay. Now, what we will do is that we will now study intramolecular in reactions, which are like that also another good class of in, lot of reactions you can do with this intramolecular. Okay, for example, I would take this is a very good example to understand intramolecular in reaction. This is deuterated. Okay. Now, if you carefully watch this, see this reaction, what will be your first step? Because you might, since it is today we are talking about in reaction, you should know that this is your which should be your in and what we are talking about, okay, which should be a dienophile and all these things. First step, what happens is this in this intramolecular in reaction, you get a proper enolization, right. So, if you get an enolization, then what will happen? Like I can have a double bond here, okay, my phenyl, and that is why I deuterated. So, your deuterium moves across, then you have your then you can think about a double bond here, right. So, now you can think about your in reaction, because you have now your all your diene as well as your in is there. So, now you can nicely do your in reaction. So, what happens? So, this can take it up, and then you can have this part. So, which will give you methyl carbon with the phenyl, you get a CH2T, right. This is a very good example for your intramolecular enzyme. So, your first step is more like your enolization, okay. Then you carry out your in reaction, right. We'll take one of the good synthetic utility of this intramolecular in reaction. What is this compound? R citronol, right? Citronellal. Have an R citronellal, okay, and this when you slightly warm this using zinc bromide, okay, it undergoes a type of in reaction. The mechanism we will study later. So, just undergoes a nice in reaction. What you get? So, very good synthetic utility method for making. You have studied this reaction, which you get to isoplugol, right? Get isoplugol, and this in reduction. What do you end up with if I reduce this? So, you end up with your menthol. Very good, very good synthesis, because you take your citronol, you do a in reaction to isoplugol, and then you reduce it, you end up with a menthol, and this reaction, the stereochemistry is properly preserved. So, we will see that how this reaction works, how the stereochemistry is maintained nicely. So, if I take this product, so called citronolol, or citronol. If I take acetonol and then if I treat with zinc bromide, what will happen? If I treat with zinc bromide, you know it complex with your key oxygen, right? So, I can write that step. ZPR2 see, after this I can do my ene, because I can I have my allylic hydrogen here. Okay. So, what happens, I can take this, I can cyclize, right, to get me my isoplugol. So, I get this, because this is a proper ene, okay, you get that is fine, but how you get this product, how to see? You can basically look this compound, understand how the transition state looks like, because you can think about writing it in a chair form and see how the stereochemistry. If I want to write this properly, then how I can think of. So, this part, then I have my double bond, then you have your oxygen, and this is the hydrogen I am talking about, and it is zinc bromide. Okay. So, now we will fix your methyl, because methyl should, you know that it favors equatorial. I have my hydrogen here and I have my hydrogen here, right. This can be drawn like this in the transition state, how it looks like. Now, if this cleaves, so finally what I should get after the ene reaction, I should get with my methyl in the equatorial, fine, and my, this should be my double bond, and with my hydrogen, I have this hydrogen here with my OH. See, this is more or less similar to this structure. Okay. That is why you get one type of product here, okay, isoplugol. You take R-citronol, you get isoplugol, and then you reduce it, you get your menthol. Okay. Best way of looking into this. Fine, any doubt with this? All right. Okay. Okay. Now, we will see some more examples, okay, which we can work on, some nice examples. we take this compound. Okay. Now, what happens? The first step, you think about the ionization, right? So, what you end up with then you end up with, if I analyze that, I have a double bond and then I have an OH. This is a nice reaction for practicing your ene. Intramolecular ene is, that is why very nice to practice. Get a system like this. Now, you can think about your ene. So, that is easy, this hydrogen grabbing and then up with this, giving you a system, a nice product. Oh, sorry. See, basically you have your methyl outside. All right. You have your methyl outside with your 5 member ring, 6 and 5. And sorry, like carbon, not 5 member, 6. You have like 5 system with your methyl out. Yeah, this example you can work on, see what you are getting. This is a very good example to see your ene reactions. Okay, you have this type of system. Can you think about what product you will get? See, the first idea is that first we have to figure out whether this reaction goes in ene. Since we are studying for today's class, we know that this reaction goes ene, but once it is given in with other reactant components, or can you find out in that paradigm where this ene reaction is, that cascade may. So, I can take this. So, what product we will get? It is a nice 5 member ring, right? See, I get a very nice product with your ene reaction. So, now we are seeing ene reactions mostly with your type of alkene, right, double bond system, alkene systems. Okay. And there are few examples where ene reactions goes with your alkyne system also. Okay. Where your you can talk about the alkyne also in ene reactions. Okay. So, you can see in this example. So, this type of system, if you notice, you have an alkyne in this case. Previous case we were talking about alkene systems. Okay. Alkyne system. When you are talking about alkyne system, when you make a cyclic member, you should think about whether the ring double bond goes outside or inside. No? So, if you think about this reaction, oh sorry, you cannot do any ene here. Okay. You have to do an enalization. First you do an enalization. Okay. Once you done with your enalization, then you can always figure it out. You can see your double bond outside ketone and phenyl. Okay. If you have a methyl here, this type of methyl systems, okay, if you have methyl, oh sorry, without methyl, yeah, you can get this type of nice products, okay. No need to have methyl there, sorry. Fine. One more system, one more example we can take about your ene is that you can take this product yeah, get me the product, what product you will think about. If you carry out a ene reaction here, so it should be what? So, are you getting I think you get like this. Okay. These are two with your alkene systems, very examples of your intramolecular reactions. Okay. So, what we have studied is that you have studied like ene reactions and then you went to carbonyl ene. Okay. Then we studied about your intramolecular reactions. Okay. Have you heard about retro ene reactions? There are another class which we call as retro ene reactions. Any simple reactions comes to your mind? A retro ene reaction. Can you relate any simple reactions with your retro ene reactions? Can you figure out any reactions which are well common reactions which can be categorized as retro ene? Your simple ester pyrolysis. Okay. You take an I will take a system. Fine. If I eat this for 400 degrees Celsius, we can correlate this reaction. I can easily do the retro part of it. So, what I end up? So, I end up with an carboxylic acid plus my alkene. Okay, this is your ester pyrolysis. This is nothing but it is a retro ene reaction. You can just look them as a retro ene reaction. Right. There are other retro ene reactions you can think about. See, instead of this ester, okay, if I take thioester, instead of that ester, if I think about thioester, any reaction comes to your mind, right? If I have a system like this, famous reaction, anything comes to your mind, name of the reaction, this reaction, instead of an ester I have taken a thioester. Nothing but it is a Chugge elimination. Chugge elimination is just falls under retro-ene reaction. Okay. Yeah, whenever you think about it, just remember this type of reactions. Your ester pyrolysis, thioester pyrolysis, that is Chugge elimination, is nothing but it is an ene reaction. The mechanism is, you can think about the same way as in the earlier case. So, you end up with your thioacid. In previous case, you end up with a carboxylic acid. In this case, you end up with your thioacid and your alkene. Fine. I think this you guys should remember about this type of reactions, which is minus. Okay. So, this you guys can remember. What is this? If I eat this, what will happen? Any idea what reaction is this? Nothing but your cope elimination, right? The cope elimination, just for example, you can have this O minus with abstract hydrogen, you can positive charge, yes. Gets your hydroxylamine and you end up with your alkene, your cope elimination reaction, that also falls under retro-ene reaction. Okay. One more retro-ene reaction which you know is that cleavage of beta hydroxy ketone. So, I can have a beta hydroxy ketone and if you heat this reaction, okay, same way. So, you end up with an allyl alcohol, vinyl alcohol plus your ketone. So, these are like very nice reaction of your retro-ene. In a retro-ene we have studied your ester pyrolysis, okay, which gives you a carboxylic acid plus alkene. Then you studied your Chugge pyrolysis, which gives you a thiocarboxylic acid plus alkene, cope elimination which gives you an hydroxylamine plus alkene, cleavage of beta hydroxy ketone, you can end up with an vinyl alcohol plus your ketones, right. So, this about your ene reactions, you just this more about ene reactions. So, what we talked about in ene reactions, we said that if you take an ene reaction, you can look ene reaction mechanistically as 1,5 hydrogen shift. Okay. and same way you can visualize in reaction as a Diels-Alder reaction. Okay. So, one of your is diene, which in reaction you call as ene, okay, that is your 4 pi electron system, and you have the another guy is your dienophile, which is normally like your alkene. Okay. So, it is again a reaction with 1 5 and it is more like a suprafficial. That is why your HOMO-LUMO, if you compare your HOMO-LUMO interaction of your Diels-Alder with your ene, more or less they are same, and it says it is suprafficially allowed. Only thing is that it is pi 2s plus pi 2s plus sigma 2s. You have a sigma into the system, okay, that 2 electrons. After seeing your ene reaction, we went to your ene, that is your dienophile can be also an carbonyl system. So, that becomes your carbonyl ene reactions, and you have lot of examples on carbonyl ene reactions. Then we slowly went down and looked into your intramolecular ene reactions. See, this intramolecular ene reaction is one thing you have to keep in mind, is that the first step is more like an enolization. Once you get that enolization, then you understand that this is more like an ene. Okay. That part should come into your mind. Now, once you do that, once you are ene, then it is an proper, you can think about intramolecular ene reactions. After that, we slowly covered your retro ene reaction. In retro ene reaction, you have started studying understanding ester pyrolysis, Chugave elimination, cleavage of beta hydroxy ketone, and your Cope elimination. So, that is more about your ene reaction. Fine. So, what we will do is that now there is another. So, in 4+2 cycloaddition we have seen Diels-Alder, we have seen your Alder ene reaction. Fine. There is another important reaction in 4+2 cycloaddition, that is your 1,3 dipolar cycloaddition, very important reaction. Okay. I will just give an introduction now. In next class we will see in detail, that is 1,3 dipolar cycloaddition. See, normally in Diels-Alder type of reactions, you are trying to make 6-member rings, right. You have a 4 pi system with an alkene, you always try to make a 6-member ring. 1,3 dipolar cycloaddition, that is why it is very important, because you try to prepare 5-member heterocyclic system, that is very important in 1,5. You end up with you can preparation of heterocyclic five-member ring systems. So, you can think about making molecules of heterocyclic 5-member rings. That is why 1,3 dipolar cycloadditions have more synthetic utility, they have been used a lot. Okay. If you see the reactions are as straightforward, like you have a system like A minus, just make a heterocyclic, okay, plus I have an alkene, fine. So, with this you end up with a general representation. Okay. Your A, B, C can be your heteroatoms, okay. But general representation you have a type of. Now, what you call them? See, this is basically what system it is. Your ABC, it is a 4 pi. Okay, it is a 4 pi. This A this is nothing but it is a 4 pi electron system. Okay. 4 pi electron system, and this you can call as 1,3 dipole. Okay, this is is called as 4 pi electron system, and we also call them as 1,3 dipole. And this is this particular alkene, it's now it is a 2 pi electron system. What do you call them? Because normally we call as dienophile. Okay, in this in Diels-Alder reaction we call them as dipolar phile, because this is dipole. Okay, they are dipole. So that is why you call as dipolar phile. So this is your 1,3 dipole, this is your dipolar phile. And again, if you see, it is a 4+2 cycloaddition system. So that is a small introduction about your 1,3 dipolar cycloaddition reactions. So again it is a 4+2 cycloaddition. So in 4+2 cycloaddition we have studied Diels-Alder, we have studied alderene. Now we are going to, in next class we are going to study on 1,3 dipolar cycloaddition reactions. Clear? So we will end up our class with this today.